With the real matrix, eigenvalues come as complex conjugate pairs. So let's look at the case of a real matrix. We can just look at a two-dimensional subspace because eigenspaces are invariant. So we have a eigenvalue and real imaginary parts, and we have eigenvector, and write it in terms of real and imaginary parts. The real part of V, the imaginary part of V. So my claim is this commutative diagram is accurate. So my new basis will be the real and imaginary parts of the eigenvector. That'll be my new basis. First thing, I've got to make sure that that matrix is invertible, or that those two vectors are really linearly independent. Instead of saying real and imaginary, let's just call A and B. Make our life a little simpler. Set up a linear combination. If they're linearly dependent, C1 and C2 are non-zero. So if I scale an eigenvector, still an eigenvector, so here's the clever scale I'm going to do. C2 plus IC1, I'll use that complex scalar. Expand the multiplication. The real part and the imaginary part is 0, so this is a real vector. But if I feed a real vector into a matrix with real values, it's a real vector. Take a real vector and scale it to get a real vector, the scalar's got to be real. But we know that lambda is complex. So, if the real and imaginary parts of the eigenvector were linearly dependent, that leads to a false statement. So they must be independent. Let's just do an example to illustrate. I'll have you prove it as homework. So we have a transformation, and it's got eigenvalues, 1 plus or minus I, with corresponding eigenvector, 1, 2, plus I, 1, 0. And we want to find t. There's my real and imaginary parts, so that's going to be my change of basis matrix. Alpha minus beta, beta alpha, they're both 1s. Change of basis matrix, and compute the inverse. 1 over the determinant, flip the major minus the minor. And we'll find what t is. So I feed E1, we'll run it through the inverse matrix, giving you the first column of the inverse, 0, 1. Feed that through, so that's the second column, 1, 1. And then feed that through B, 2, 2. So there's the first column of my T matrix. Now I'll do the same for E2. Feed it through the inverse matrix, 1 of the first column minus 1 of the second column, half that. So negative of the second column of B, there's my second column of T. Just a quick check that this commutative diagram is true. If this was T, then the determinant of T minus lambda I should be 0. And I complete the square. And lambda has to be 1 plus or minus I to make that work. So that's nice. Let's check that 1 plus I over 2 is really a eigenvector. Feed it through T, 1 plus I of the first column, 2 of the second column. Compute. Compute. Well, that doesn't look like the same vector, but we're doing complex arithmetic. So if I pull out 1 plus I, there it is, because 1 plus I squared, 1 plus 2I plus I squared, which is negative 1, is 2I. So TV is lambda V. So this is an eigenvalue eigenvector pair for that matrix. Compute the eigenvector by finding the null space of t minus lambda I. So we set it up. Since it's a 2 by 2 matrix and it has to be non-invertible, we already know the second row is going to be zeros. But a quick verification, if I do this minus 2 over 1 minus I scale, it zeroes out. Solve for V2. So my eigenvector V2 gets replaced pull out a V1. Well, that doesn't look like the vector we just had. So we're saying the eigenvectors are in the span of 1 and 1 minus I. But this is complex arithmetic. It's a complex span. If I multiply by 1 plus I, I get the eigenvector we had before. Say I still didn't believe it. I can still use this eigenvector for getting my change of basis matrix. So we have our T matrix that we use to find this basis, compute our B inverse matrix, and you get the same matrix out. That's kind of neat. So now let's compute the implied transformation. So I'll send E1, gives me the first and second column added together, send it through B inverse, and there's the first column of the bottom transformation. Do it with E2, send it through, send it down, same matrix.